Uh, Hello everyone, and today we are talking about discussing inductive representation learning on large graphs. First of all, my name is Parham Hamouni. I'm an applied research scientist with Creator Lab. It's a pleasure to be here with you guys. So it's a 2017 paper, and I will be presenting it to you, and Karim Kharet, who is a data scientist at BMO, will help me and help you with the questions. So first of all, we say it's like GraphSAGE, it's based on networks. So the question arises, why study networks at all? So because, there are lots of examples of networks that can provide us with a good amount of information of the products that we need in AI today. For example, we have social networks, which we have a lot of different uses potentials with it. We also have web, the most obvious monetization would be like Google. You have molecule representations, far more interesting in the pharmaceutical businesses, and also knowledge graphs. You have all the information between the people, so you'd want to essentially derive an information from this structure. And it's somehow the new emerging data format in the data science market nowadays. So what we mean in networks, if you want to put it more mathematically, it's essentially graphs. Even recommender systems that you're most familiar with mainly, essentially connected together, because in the recommender, traditional way was based on, we had this feature representation. For example, you have the NLP that tries to capture the words, and make them into representation. Then you have this network representation. That is, we try to capture the information from the graph in a systematic way. And what is that systematic way? It's like first trying to represent it by a matrix, which can be like the adjacency matrix, or then graph Laplacian matrix in other terms, which represents the information of the graphs and its connection. So what is, for example, graph adjacency matrix is a matrix that will provide you with the information of whether each node is connected to one another or not. If a node A is connected to node B, in the A, B row, there will be a value of 1 and otherwise 0, right? Any question until now? Okay. And graph Laplacian is like another type of representation, which is essentially the difference between the degree matrix and the adjacency matrix, and has been proven in graph theory that there are some kind of, you can capture better representation of the graph is like more invariant. And then we try, what they did essentially was using this feature representation, try to capture that based on this Laplacian matrix or adjacency matrix, try to find representation. Then we have this representation. We also have the feature representation, for example, in Twitter case, TF-IDF, Doc2Vec, different sort of word embeddings. Then we concatenate them together, and based on the classifier, we'll assign the nodes and labels, right? That was a traditional one. So the whole idea is that we want to assign, first of all, a vector node embedding a vector to this node, and then based on that embedding, we want to do a classification, right? So for example, this embedding would provide us with the information in Euclidean space, and then we can go. So that's the whole picture of what is the objective that we want to achieve. So everyone okay with that? Okay. So the naive approach would be like just trying to capture the information from the adjacency matrix and then pass it to the features without any node embedding, and then pass it to a neural network, for example, to find the predictions. But there is a problem with this naive approach. The problem is that since the node adjacency matrix is variant, it's not invariant. That is, you can have different node orderings, and it won't change the information. What I mean, for example, imagine that you have a graph of 10 nodes, and then you have named them 1, 2, 3, or so on, based on random ordering, right? The first time you got information from. But it doesn't provide you with the true place and any ordering or any hierarchy, any information of where is that node located in the graph, right? So if I, for example, changed 2 rows of this matrix by renaming, you would have a different representation, but the real graph hasn't changed, right? So we want to have, and since the data is non-Euclidean in that space, that is that you cannot capture the distances of each entity by using similarity functions which are applicable in the Euclidean space, like norms and like distance and like cosine, that sort of thing. It is not possible to capture information correctly by neural network. So we need to represent this adjacency matrix with a representation that will embed this node into a Euclidean space, okay? Which we have this similarity and other measures that we can apply to it, right? So there's this type of lots of work on this node embedding techniques like node2vec or deepVoc. I guess you have heard of them. So the basic idea is that now we want to have this representation of the network, and we have the graphs. Whether we try to apply the success of deep learning and try to find out this CNN-like architecture that tries to capture the information from the adjacent nodes and put them in a similar embedding. What I mean by similar embedding is that the embedding of, for example, this node, which is adjacent to this one, which is neighbor of this one, is closer in distance in that Euclidean space. That is the idea. So how we do it in CNNs? We apply a filter. This filter tries to capture the local information, and then it somehow rolls over this matrix, which is like a grid, and then it captures the information and passes it to other layers, right? But how about if we try to apply a filter on graphs? Since you have different adjacent nodes, that is, for example, in here, this one has 1, 2, 3, 4, 5, 6, 7, something like that, adjacent nodes. The other ones has 2, 3, 4, so you cannot apply a fixed size filter, right? So we have to come up with a more creative way to capture to apply this filter and capture the information which are close to each other, right? So, for example, GCN, which is like graph convolution network, is one of the earliest, not earliest, one of the successful ones which happened in 2016, and we already discussed it in our Lunch and Learn with Ace. You can watch it if you like. So what is the difference between GraphSAGE and GCN that we already talked about? GraphSAGE has the same mathematical explanations as GCN graph theory, like it's based on spectral graph clustering and Weiss-Fire-Lehman algorithm. If you like, we can go through that in discussion points. It's essentially a variant of GCN. And the problem that GCN had that it tries to solve is that there was memory issues with GCN. And why is that? Because it wasn't possible to batch the network, because each time what it does, essentially, if you go here, it has the whole graph. It tries to assign each a single shared value for each node. So it should have the whole graph to do such a thing. But if we want to tackle that, GraphSAGE is with its sampling and aggregating technique is the way that we can use it. So it essentially tries to address the limitations of GCN. Okay. So if we go here and see how is the architecture of the GraphSAGE, what we have is like you have this graph, and then you want to embed the information of the nodes which are adjacent to this one to a closer embedding. And what you do is like you try to sample through the adjacent nodes of that graph. Instead of having all of it and try to do a computation, you try to sample it. And if you're doing by sampling a fixed size, then you can have a batching algorithm that corresponds to it, right? Because when you have this fixed size, then you can pass it through batches to the network and it then tries through there, right? So we sampled the neighborhoods, so the question arises, what is a sampling technique and how we can deal with that? So that's a question I'm going to later answer. Then, so what we did was right now we just sampled some nodes from the graph. So what we do with them, right? So we want to say that, okay, if we try to aggregate the information of these nodes, what we will have is that the embedding would have captured the effect of other nodes as well. So what I mean, imagine you have 10 numbers, right? So if you try to do a mean of that 10 numbers, what would it be? This index, this mean operation, would aggregate the information of these 10 numbers and try to assign a number, output a number based on all of the information from other nodes, right? So what we do here is the same thing. We try to aggregate the information in here. So the question could be, what is the aggregator function? Which one can be helpful to us? So we sampled, we aggregated the information, and then we try to pass it to different layers of a neural network to assign a label to it. That's the whole overview of the algorithm. So any questions by far? We're good? Okay.
To the nodes that you like, or it would be like any nodes within that section that you're considering?
What's that again?
For example, if you have like two circles like over there, so layer 1 and layer 2.
Right.
It will only include all the nodes which is connected directly to your node, or could be like any node within that region?
It depends on the search depth that you choose. For example, in here we have chosen a second, k equal to a depth search of 2. What that means, these are the first order neighbors of this graph. So you have this red one, and you have this pinky one, which are in here circled by this circle, right? This is the first order. And then we have also a second order, that is the neighbors of that neighbors, right? Depending on what is your task, you can play with this number of the search depth. And essentially, the number of layers in the neural network that you will have is this search depth. Why is that? Because each time we'll sample the information from the first hop. This is called hop. I mean, the first order is called hop. You have this information of this first hop, and then you try to do this aggregation. Then you go to the second convolution layer, or I mean, like aggregation layer. So we'll do it again. So the information that you captured for the first layer will, for example, for this one, would also capture the information from the other hop as well, because you have already done it twice. So information once came in. You're passing the information essentially by adding different neural layers. Is that okay?
Just to sort of elaborate on that, I mean, remember the example that they talk about in the paper is that you're thinking of the hops as a context vector, right? So you're expanding the context
exactly
with each hop as you're embedding, right?
Exactly. Okay. Any other questions? Okay. What? Okay. Sorry. So again, if you want to have an overview and understand to summarize what we are right now in, we have a node we want to assign a node representation to each node based on the adjacency and the structure of the graph. So that's the task that we are dealing with. And also it tries to assign closer values closer in this space that we have. And I told you we take the distance, for example, as a way of closeness, measuring closeness. That has more connection in the graph to one another, the Euclidean. That's the whole idea. Okay, we try to assign values which are closer to each other in the Euclidean domain as a way to have a node embedding, okay? So what are the benefits of GraphSAGE, this architecture? So as I told you earlier, it will reduce the memory footprint by making batches through sampling. It also uses multiple aggregators rather than just simple convolution in GCN. And then so these are the like benefits. And what is the sampling method? I'll tell you, in GraphSAGE, they will just go through the uniform sampling technique, but they mentioned that in future work we would like to try to extend and test different sampling techniques and find out how they would affect the architecture. And now the question arises how to aggregate information to provide corresponding embeddings to similar nodes, right? So we have covered the sampling part. Now the aggregation part is the problem that we try to see. We have what they propose. Yes.
Just one question. So you sample a specific number of nodes around your target node in a like neighborhood kind of.
Yeah, exactly.
So in the previous example, you were sampling 3 nodes, and in a neighborhood of 2. Like how would you describe this diagram in terms of the sampling procedure that you just described?
What's that?
So, for example, here, let's say you chose k to be equal to 2, right?
Right.
But I'm assuming you're also supposed to choose how much you're going to sample. Did you choose to sample like 3 neighbors, or did you choose to sample 1, 2, 3, 4, 5, 6?
It's actually just like as illustrative. It doesn't exactly correspond to the algorithm, but you have a fixed size sampling size. That's the idea.
Okay.
Sorry, I think his question is whether you apply multi-step sampling or just like uniform sampling from the entire.
Yeah,
so you have 2 depths. So k equals 2. So you want to sample some nodes from k1 and then some samples from k2. So do you first sample from like the first order neighbors and then the second one, or?
Well, I will go through the details in the algorithm. I will discuss it the first one. Okay.
I think it's uniform.
Another question, sorry about that. I didn't understand the data representation that you're going to learn from. First of all, when we talked about GCN, you said that we need the whole graph as a representation, and if you change the rows of that matrix, it will change for the regular neural networks. But right. You want to find out the patterns in the whole graph, right? But right now in this kind of structure, we are working on one node and then sample around that node. It doesn't have the structure of the whole graph.
So you do it for each node as well.
So how can it be efficient? We were doing when we were learning a pattern in the whole graph. We had the whole graph. It's expensive for memory, but we are doing everything just once for the whole graph. Right. But right now we have to do it for million nodes.
Right.
And
but we can do it for
how can it be efficient that way and not this way? It's width or depth is kind of what is the trade-off between these two methods?
So when you are dealing with a large, for example, social network, so how is it possible to even load it in the memory, right? So that's a problem if you want to try to load all of the graph in the memory. So what they do essentially is that they have a node, and what they do is they sample through the nodes, and they do this process iteratively. By that, they can batch the nodes. I mean, instead of having all of the graph pass through the architecture at one time, they can try to batch it. So that way, it can learn it more efficiently. That's the idea. Okay? So, I'll go through it. So, they propose 3 aggregators. One of them is mean, the other one is LSTM, and the other one is max pool. So what is mean? The good thing about mean is that it's invariant to the sequence of sampling. That is, imagine that we have sampled nodes. There are 10 nodes in the neighborhood. We have sampled from node 2, 7, and 9, right? So it doesn't have any difference to sample this order differently, like 9, 7, 2. It doesn't have a sequence order, right? So that is what is good for us, because we could have different type of sampling, and because it's random, the aggregator function that we have could capture it. Okay, great. How about the LSTM operator? LSTM needs order, so they try to test it, and then what they try is that, so if we cannot apply this type of sampling because it's the sampling for order, right? So what they do is they have a random permutation of the samples, and they consider it as a input in the LSTM, and then try to apply this LSTM aggregator. The other one is max pooling, and what they do is essentially do the max pool. We're trying to have these samples, and then they try to get the maximum of that sample. Okay. So that's the whole idea. Okay. So the GraphSAGE algorithm has three components. One of them is this embedding generation, this process of algorithm that we're currently discussing on. The other one is a loss function, and the other one is backpropagation technique. So you have learned it, you have passed this information through these layers, and then you should learn a weight matrix, right? Because you're training something. So you should first of all have this embedding generation, then you should send a signal through a loss function by this backpropagation. Okay? That's the idea.
In the previous slide, can you explain what are the learnable parameters for each of those?
Sure.
Could you repeat the question?
He's asking what are the learnable features in that aggregator function that we have. So as you can see here, we have this W transformation in here. So we take the mean of the adjacent nodes, and also then we concatenate it with the node itself from the previous layer, and then we take the mean, and then we apply this weight matrix to it, which is learnable, and then we apply this sigmoid function, and then which is linear, and we pass it. Right.
The dimensions would be the number of samples, so it's fixed.
Exactly.
Okay.
I think the weight is the size of the features of the node, not the number of samples.
Okay.
Well, there'd be both. It's just depending on the match.
No, but because he's taking the mean, right? He's taking the mean over all samples, so it's going to, so the weight is going to be the size of the features.
It would be one-dimensional. Yeah.
He's right.
Yeah. I mean, you could batch it.
Okay. So so if you want to go through it formally, what is the GraphSAGE embedding generation? You are given a graph with, this is called G, and you have input features which are like a node features. In our case, it was like a Twitter content. And then you have the depth, which how many hops you want to go deep into the graph. And then you have this nonlinearity function, sigma, and then you have this weight matrices that we talked about, this W. And then you have this differentiable aggregator function. The idea about mean, LSD, and Maxwell is that they are differentiable, so we can do this training by backpropagation, right? So what they do is for the search depth that we have for k equal 1 to k, that's whole search depth, and for each node, that was a question that you were asking, so how we can go through the nodes. So we do it iteratively. It's like 2 for loops, okay? And then what you tried for each, H is like the representation for each, in each depth search that we have. This H is a hidden layer, right? We do the aggregation of the features of the adjacency of the neighbor nodes, and then we concatenate it with the representation of the node itself from the previous layer, and then we apply this WK, which is the weight matrix, and then we go through this sigma, which is the nonlinearity function, and then we assign the new node embedding. Okay, so that, and then we try to normalize it. That's it, generation. Any question on that?
This iteration that I asked before,
right?
When we are sampling on a node, do we have the same samples? Like, do we have all the nodes with their samples forever for the whole training duration, or we sample again? Like, if like Trump is with Russia in one sample right now, are they gonna be again the same sample, or we randomly choose another one, like let's say Spain, other time? So is it like, do we sample again when we are training on the next epoch, or?
So for example, I'm doing it for the first time for this.
The first epoch, we sample something and we train on it.
Right.
So we want to go to the next epoch and
right.
learn more like about the network.
Okay.
The one epoch probably is not enough.
Right.
So do we sample again, or we use the same sample like?
It's uniform sampling. So so for example, imagine that if you have this node in here, right? You sampled this one and this one, okay? Then you try to sample for this layer. It's possible that you captured this node again, the previous node that you captured. look at here. Look, this one.
I mean, do we learn one node just one time, or we go through it like again and again and again?
Depending on the depth of the search, because you do it. Look in here.
I think they resample.
They resample, yes, because
Yeah.
it would be a different representation every time, right?
Yeah,
Well,
but
it's a different approximation of the graph each time.
It's sort of like dropout. Like you don't know, like you don't have this weight right now, but
Okay,
the
I'm
other.
gonna call it out. Great question. Comparative. Let's move on.
Okay. Sorry for that.
So I think the answer was. Okay, I think.
Are we moving on here or not?
Okay. Maybe just repeat the answer for the audience online. I think your repetition is on.
It's possible to. It's when you have two nodes, the sampling distribution is uniform. So we don't have any information of the other nodes when we are doing a sample for the first node. If we are doing a sampling for the second node, if they are connected, they can be both in the samples of node 1 and node 2 as well. So you can capture the relationship between node 1 in the sampling for the first node, and also you can capture the relationship between node 1 and 2 in the second one. Maybe or maybe not. It's random. So, okay. So how about the loss function? So what we did, what was our assumption? If we can go over it again, we try to assign a value which is closer when we have the nodes which are near each other. They are neighbors, they are adjacents, and then we want to make it far away from the nodes which are not connected to this node that we're trying to find embedding, right? So this one is the layer representation of node V that we are currently discussing, right? And you, and V is the representation of the adjacent nodes that we have. Okay. Then by assigning this cosine similarity, then we would have a similarity matrix, right? Then we go through this sigmoid. What the sigmoid would do, it would amplify the signal. That is, it will try to say, okay, they are more similar. They are more similar than just this cosine, because if they are more similar, it would assign higher value, right? And then also we try to do a logarithm as well. We try to assign a logarithm as well, right? To even try to make signal amplified even more, right? And then we also want to make this representation less similar to the nodes which are irrelevant to this node. So for example, imagine the Twitter context. I am connected to some friends and I'm disconnected with other people. So you want to have a representation for me which is closer to my friends and far away from the other ones that I'm not connected, right? So what we did here was we tried to somehow make it closer, the relationship between me and the people who I'm connected with, okay? And in here, what we try to do is we try to make the space, make the distance more from me and the people who I'm not connected. So how we do that? We do a negative sampling queue, and then we have a probability for this negative sampling as well. What is that? What is negative sampling? When you have a node, for example, me, I'm connected to, I don't know, you, for example, with Twitter, right? And we both, for example, like machine learning, so there's some connection, right? And then, for example, there's other person's Twitter who likes other stuff that I don't like at all, okay? So we want to have a representation which captures my relationship with him and also not capture the other person's relationship, right? And make it distant. I mean, be project. Oh, good.
No, it's good. I just want to add. Keep in mind that Z includes all the context information.
Yeah, that's good.
Right.
Yes. And
that's
then
the final output of the embedding.
Right. And then you have this negative sampling distribution as well. What I mean negative is a person who I'm not connected. So imagine that we have this huge Twitter data, and there are lots of people who are not connected to me. So if I want to try to make my representation far from all of them, it would be like, again, having to load the graph, all of the information about the graph. So it's not efficient. So what I would do is I would do a sampling, okay? So this sampling, again, is also heuristic. Based on different algorithms that we have, based on different tasks, we would have this different sampling techniques, okay? So this is the expectation of that information, and then by this minus, we try to send punish the negative samples. That's the other way to say it. We reward the positive samples, and then we punish the negative samples. Okay? So that was the whole loss function.
Is Z sub V one of your neighbors?
What's that?
Is Z sub V one of your neighbors? So node of interest is Z sub U, right?
Right.
Z sub V, is that one of your neighbors?
It is the, in here,
It's just any other node, I think.
it's the representation that we had for the adjacent nodes.
Okay.
All of the adjacent nodes, we had one representation.
For the
And then we apply like, then we got this.
Are you summing that up over all neighbors? So V was just, Z sub V was just one of the neighbors. Which one? Like you're just, I mean, are you taking a sum over, are you summing that formula over
It's
all
for
neighbors?
each node. Then we have to do it like in a matrix, right? For all of the nodes.
Okay.
It's for one node, notation for one node. So for the all nodes, you have to do it in a matrix. You have to.
All pairs of nodes, you can do that.
I think you mean U. U is for all nodes.
Yeah.
I don't think V is for all nodes.
No, V is,
Where did V come from? Yeah, that's another one.
you know, V in here is like, V is the,
Oh, okay.
it's over here. You have this representation of this for each node and for each adjacent node. When you do the mean, you take the mean of the adjacent nodes, right?
But I think it's in the later slide. So you mean the loss function, right?
Yeah.
Do you mean in the loss function or the algorithm?
In the loss function.
So do you want to, yeah, so the
So-
V there,
Yeah.
I think it just means any other node.
Any other node neighboring?
The other neighbor
Well,
node.
because but for the contrast example, for the negative examples, right?
Is V-
Presumably they're not neighbors.
The V, you know, we have V, which is like positive ones, which are like closest. We are
are
close.
neighbors,
Those are neighbors, and Vn are not neighbors.
Sure.
Yes,
I understand
there
that,
you go.
yeah.
Okay, so
But
what's
so I'm just asking, to compute the loss function
right?
on Z of U, you just pick just some random neighboring node,
Yes.
Right.
V, could be any one, you just pick one. Okay.
No,
Well,
you have a representation for all of it.
so you
have
pick
the
a
sample.
representation for one neighboring node, yes.
You have the sample, then you find a representation for all of these samples. It captures all of this. For example, you have 3, then you capture the information of this 3 node by going through this aggregate function. You say that, okay, what is the context? The context can be the mean of the information of the other adjacent nodes. Okay? No, not okay.
Yes.
No, okay.
Okay.
So
You assume that ZV is known and you're looking for ZU and ZV is coming from here.
easier way to put it.
Okay, I'll have to clarify at the end.
Look, what we did was we had the first node, right? We had this node, and then we had sampled other adjacent nodes. Is that correct? So we want to have a representation for the adjacent nodes. We pass it through this aggregation function. We would have a representation for the adjacent nodes. It's like having a context representation for the node itself. Okay.
I think the ambiguity here is whether or not, when you're actually computing the loss function, whether or not you literally check every single adjacent, like first order neighbor for the loss, or if you check a random sample for the loss, or if you check 2 for the loss. Like, do you see what I'm saying? Specifically for the loss function, not during the aggregating part. The aggregating part is a random sampling. We know that.
Okay.
The question is, if you go to the next slide,
Right.
in order to make that work, right, V, you have to have some.
Move back. The microphone is right above.
Oh, move my head back. I think the question is V. So you have a V, the first V.
Right.
Is that every single neighboring node?
No, it's sampled neighboring.
You
So
sampled.
what's happening here is that you want to optimize this loss function for you.
Yes,
So
I
you
got
want to
that.
solve for you, and your known is here is ZV, which
Right.
is calculated from the algorithm that you saw in the last slide. So you
Previous
calculate ZV, then you optimize for ZU. Again, you can go.
Yeah, that's clear. But the question is, if I have a million neighbors,
Right.
do I do
all the
all
million
a million
neighbors are
neighbors?
aggregated using LSTM or min or
I
max.
think the ones that you sample,
wasn't
you,
You know-
you aggregate information from those.
What is Z essentially is the last layer of this algorithm.
Yes.
Yeah.
So if you are okay with that algorithm, I don't understand what is the problem with that one.
I guess the aggregate part is for the neighbors and for negative neighbors as well. So I guess that's the representation. The aggregate works for the sample of negative neighbors and also the positive neighbors.
Right.
So both of them are represented by the aggregate function.
Yeah.
So
I mean,
whatever it is, it can be mean or LSTM. Like we have a representation of all the negative neighbors, and then that's the ZVN.
right. Okay.
It's not one node or two nodes. It's all the samples, negative one and positive.
Can we move forward because I just...
Yeah, move forward. Yeah, I'll ask you at the end.
Oh, yeah.
Go ahead.
Yeah, because actually it's 5 minute break. And then we have this, then we pass the signal of the loss function by back propagation, which can be this stochastic gradient descent or Adam optimizer or something like that. Okay? So that's the whole architecture. And now we go through 5 minutes here. And then we can discuss it. So they try to use this algorithm for 3 experiments. One of them is classifying academic papers into different subjects using the Web of Science citation dataset. What is that? Is that we have this network of people. GraphSAGE. Yeah, I have. Okay. Okay. So, as we were talking, they have done it for the classification of academic papers. They have used it to classify Reddit posts as belonging to different communities because of the connections that they had, and classifying protein functions across various biological protein-protein interactions. So, the difference between the third task and the other ones is that we already know the connection between, for example, some nodes to other ones. We have the structure of the graph. Maybe we are trying to find the labels. Some of them we have, and some of them we don't. It's like a semi-supervised setting. But in classifying protein-protein interaction, we are given a protein as a graph, the informational protein. Imagine they have like this chemical atom C and M and H. The molecule is represented like a graph. And then based on this graph, we want to, and which has a label, then we want to find out the label of a completely unseen graph. That's the idea of inductive learning. So that's why they say it's like inductive learning. That's why the title is inductive learning, okay? And in all these experiments, they perform predictions on nodes that are not seen during training. And in the case of PPI, they tested entirely for unseen data, which is like the inductive learning, okay? So, for all of these, they tried this algorithm with different architectures. They also applied which is called GraphSAGE GCN, which has essentially the same convolutional structure as an aggregator. Instead of having like instead of having mean and max pool and other things, they just use the convolution operation the way that GCN did, okay? But what is the difference then? The difference in the sampling method that they use. And then they also use other types of baselines. One of them is just picking a random label. The other one is using the raw features and just without any network representation, just fit it to a like logistic regression function. The other one is using deep walk. It's like using a node embedding technique, and then based on that, try to classify it. And then they also try to concatenate deep walk with features as well, and then they try to do the comparison. And the comparison is micro average F1 score. So what they come up with is that they would have a much shorter time for training it. And why is that? Because for example, in comparison to deep walk, and in deep walk, because you have to, again, when you have a new node coming in and new structure, you have to, again, retrain all of the network to capture that. But in here, because it captures the context and relationship of them, and also uses sampling, this training can be like in much shorter time, as you can see here. And also the neighborhood sample size, they have also tested it, as they show after some time, number of more than 50, there is not much of a difference between sampling size. So with 50 samples, they will have like an okay estimate of what's happening. You don't need to make it make the sample size extremely huge. So that's why it would help you. What?
So this 50, is it like the number of, like the depth at which you sample?
No.
Or the number of nodes that you
The number of nodes.
Okay.
Depth is maximum, that is 2, right?
It's K. Yeah. I'm not sure about the architecture they use, but they have tested multiple architectures. Yeah. They found it on a cipher parameter.
So it'd be breadth at a given layer.
Okay.
Probably. Thank you.
And then, and as you can see, the runtime increases dramatically with the sampling size, which is obvious, right? But then you see that there's a trade-off. You don't need to sample too much because there will be like runtime associated with it, right? And they, what they show is that GraphSAGE, different types of GraphSAGE structures shows better performance rather than the traditional models. So if we want to have a summary and take away from this presentation, for most of the contextual products and recommender systems, graph networks can be used as a mathematical tool. You can try to apply it for that type of tasks. And GraphSAGE is one of the successful approaches that has been applied for graph representation in general and trying to have classification and labeling of graphs. And because of this batching techniques, it can also be applied to large graphs as well. And the sampling method can be improved later because, depending on the context, having a uniform random sampling cannot be, maybe not the best case. So it's dependent on the context. So that's why, for example, for a negative sampling, they propose a heuristic methods, for example, and how to do the sampling of negative ones and the positive ones as well. Okay, so about the discussions, because I talked about the, it has this mathematical proofs of spectral graph clustering and why is too much ease? Why is the Lehman algorithm? And if you want, we can go through them as well. And the difference between node embeddings versus GraphSAGE and whether they have better performance or worse performance and the sensitivity of the GraphSAGE to the content as well, and other sampling techniques, how could it affect it? I mean, what are different contexts? Do you have any suggestions, for example, for a given task, what should be the sampling technique? And maybe why not having a workshop on it and go deeper to this graphs, all these graph networks, because they can be quite useful. Maybe we should have a discussion with the aggregating select. Thank you. And okay, so have your comments on it.
Okay, so there was a question that I cut off earlier. You draw a comparison between Dropout.net and this?
Yeah.
This is the time now.
Okay, thank you. So basically,
No, I was just, okay, go ahead.
So what I didn't get from the process of training this network is that for each node we want to learn about the representation around it, by sampling, first hop, first level, second level, and do we just do this once for each node, or we repeat that 100 epochs for each node? If I want to learn about Trump, do I go and learn once and sample it for the K1 and the K2 and done? Or I just do it iteratively?
So when you, for example, for node 1, you have different samples and you try to get, right? When you say
for node 1, we have
you have one
samples
sample
and we have the loss function and everything, right?
And
we just go and back propagate and done.
Okay.
Are we going back to this node again?
For the second K, we go through that. But
for the second time, right?
Yeah.
No, not for the second K. For the second K is the second hop, right? So it has the second level.
What's that?
Epoch, not K. The second time you go through the whole epoch. The whole time through the database.
So the K2 is the second order closeness of the nodes to that node. But that's good. We go towards all the Ks. But after that, are we going back to this node to learn about it or not?
So the uniform samples of the neighborhood, are they fixed at every epoch, or do they change at every epoch? And I think they change at every.
Because, for example, you have this for the node. For example, the first node. You have done this operation. Why should you do it again?
Because it's the learning. When you're learning a classification for ImageNet, you have one image.
Right.
Do you just go through it just once? Or you give it 100 times, 100 epochs, and then you go back to that image and image and image, and then you finally say, okay, I'm learning something here.
So,
It's not like if I show the network once something that's done, right?
Can I interject? I think this could help. I'm pretty sure you get the answer to. So, correct me if I'm wrong. I think the difference over here with the other image classification and maybe other NLP tasks is that you don't iterate the same way you would do. And the reason is that you have a restriction. If you iterate too much, you're going to basically, your node's going to have information about the rest of the graph. And that's undesirable. So usually you had a number, like after two or three hops, the performance will drop. So I think what happens is that you have k equal 1, k equal 2, right, per node, right? So per node, you do it twice, and that's it. Is that a fair?
I think his question is about epochs. Like when you're doing gradient descent, you don't do two steps. You probably do 100 or like 20.
So okay, you have this batch size. For example, you consider 20 nodes, and you do the sampling, and then you train the loss function, and then you go again onto 20 other nodes, and you do it. That's the question, right? And that was the answer, right?
So when you get to the same node again, say you.
So why you should get to the same node again?
Get back to the node again.
Why should you go through the same node again?
On the next well, if you're on the
next K, you will go through that.
So I think the answer you're giving is that the epoch is like, so you sample from each epoch, you sample from the rest of the nodes.
So there's no epoch here, right?
It is, but you sample from the rest of the nodes, not the ones.
I mean, if you call it epoch, it's not epoch.
Yeah.
Yeah. No. I agree with you.
Can you go to it's not epoch and it's just twice.
Pseudocode? Yes. That's it.
Okay.
So you're good?
Yeah.
I didn't get what answer was satisfactory for you.
Yeah, it was, because I thought there was like there's supposed to be epochs in this kind of learning, but apparently I didn't know that.
Yeah, because I think the premise, and correct me if I'm wrong, the premise of epoch is we trained on the entire data set. Now you want to train it more and hopefully refine your representation, right? But that's that's damaging for this case. Like you don't want to revisit the same node too many times.
Actually, the questions are different. I'm understanding is that, correct me if I'm wrong. My understanding is that you say that, for example, for the first time we are going through this graph, right? We take one sample and then we do for all of the nodes. And then you say whether we come back again to it for the second time on this task.
Yeah.
If you go to the second K, what you would do essentially is the same thing. And why,
No, I'm not talking about the second K. That's the thing.
So
when you're done with the second K, you forget about that node and you have the representation of that node. That's all. That's what Hassan is saying.
So can I just clarify this? So after you go through K1, K2, this forward step, okay, you run your back propagation, you update the weights, right? Now, next step, right? When you sample again, when you do the neighborhood function sampling, is the neighborhood for every node identical to the previous?
We don't have information from the previous steps. Okay. We don't store the information.
The neighborhood is different on every iteration.
Right.
Exactly.
It's random. Yeah. It's random.
Every iteration between every epoch is different. Unless by fluke it's the same.
Hassan is saying there's no epoch?
No,
there is an epoch. There is an epoch. Why shouldn't it be?
He said because it would be damaging. Like
no,
it will
that's completely different. But look, Masoud. These are two different problems, and these are two different answers. What he's saying is that if we increase this K to, for example, 10 Ks, what would happen? You would have the information from the K hop pass to this node.
Yeah, that would be too much.
That would be too much because it was like noisy. Because, for example, someone who's friend of my friend doesn't have any information about
me. I'm good with K equals 2.
Okay, that's fine. So we're done with it. Yeah. The second question, you ask whether it's possible to we have epoch signed or not.
Yeah.
Of course it's possible. Okay. Why shouldn't it be possible? Because you have the sampling once, then you have this node batches, you can pass it, you have your epoch, then you go through other nodes, and then you go to do a sampling.
Every time we see a new representation of the neighbors of that node.
You do it you do it once for the whole graph, for the whole nodes. And how you do it by having epochs of small batches. For example, you have 1 million nodes, you will batch it to 100 nodes, And then for that 100 nodes, what you do is you would do sampling, you would do aggregation, you would learn some stuff, you would send some signal to a loss function, you do it for the second 100 nodes. Then you do it for the third 100 nodes. So for each k, you will just visit one node for once, not twice. If you visit it twice, you will go through the second k. Okay? Good? Okay.
We'll talk after.
Yeah, I just think that this picture is a bit misleading because like it almost makes it look like on k equals 2, you're looking at the same kind of routes.
Yeah.
But actually, you're only ever looking at your nearest neighbors. Yeah. And then so on k equals 2, it's a different set of nearest neighbors. But now those nearest neighbors have information about their neighbors. That's how you see them.
You have this fixed random walk length, so
yeah,
they're just taking that.
K equals 2, like it almost looks like that you're going to look at the same neighbors on the second iteration. That's why I think that image is slightly confusing, and that's just a comment I have.
Yeah. Tell your Leskovec and the authors.
Yeah, I think you mentioned it's not only first and second.
Can I ask a question? Yeah. Okay. So since they are limiting the neighborhood, the sampling neighborhood to 2, aren't you worried that you will not contain much context information from nodes that are further away from you? That's
if you go too far, if you go too far, the information will be too noisy. Why is that? Imagine that I have this graph representation of social network, okay? And we want to pass the information in here. You see the sample source. So imagine that we're friends on Facebook, right? And then you have another friends whom they're not connected to me. So it's like in my second hop, and then that is like if you go for third hops, it's like trying to find relative information to me based on the information of friends of your friends. Yes. How they're relevant to me, That's why if you go too far, it's like the information would be like not indicative.
Maybe in the social network context, that's true.
Right.
But what about, I can see that, for example, when it comes to Reddit, it may be different. Maybe with protein interactions, it may be different.
So that's a hyperparameter. But what they have tested is that if you go too deep into this graph networks, it won't provide you with useful information.
It will easily end up being every node having information from the rest of the network.
Right.
Because let's say your first K, you get information from your neighbors, right? But your neighbors are also getting information from the neighbors. So the information can propagate easily from the rest of the network, even with 2K to your node. So with that, you usually get too much information. So
you mean if you have multiple layers in your network?
So you do have Ks, right?
Yeah, but if you have too many layers, then you have a homogeneous representation at the top. So if you take the max, for example, if we max pool at the top, then a lot of the nodes will end up having the exact same numbers.
So how could you help it with the clustering and differentiate it between the nodes based on their structure?
No, I'm saying that's a limitation of having a deep structure with a max pooling aggregator, for example.
Yeah, if you put it too much, then exactly the same way you said that. If you have it too much, all of them would converge to somehow similar numbers. So they will be quite close to each other. So it cannot help us to classify and differentiate between the nodes based on the structure of the graph.
Okay, so that's sort of like a trade-off between the number at the neighborhood and the depth of the network, I guess.
The neighborhood?
The depth K.
Correct.
Okay, fair enough.
Can you clarify the inductive case with an example?
Sure. Inductive layering in general?
No, for example, protein interaction.
So what they would do is that they would have a representation for the whole graph. Why is that? Because for each node, you will have an embedding, right?
So nodes in that graph for a protein, what are they? They're atoms or?
Yeah, they're graphs are atoms. So based on the relationship, for example, like, I don't know, this carbon has a relationship with hydrogen and so forth. So that's why you have this molecule which is represented by graph, right? Okay. And then you have other molecule which is represented by different graph. Then you want to find out whether they're similar, or whether they would cure the same disease or not. So because of the structure that they have, these graphs have, you could estimate whether it's possible or not.
How does that work?
So you have this node embedding, right? Then what you did was you assigned the unique node embedding. You try to assign a unique node embedding for each node, right? You have a vector which is unique to that node. It's like an ID of that node. Okay. Then you have this matrix of the IDs of the node, right? If you have another graph, you will try to find IDs for the nodes of that graph as well. So by comparing these two, whole representation, these matrices, you can find out whether these two graphs, which are molecules in here, are close to each other or not.
Are they like feeding it to another network, or
Yeah,
how do they measure the
So,
distance?
for example, you have 20 proteins, and you have the labels as a training set. You learn the embedding for that 20, for each graph, for these 20 graphs, and then you pass a completely unseen data. Instead of a graph, imagine that you have an image. You have pre-trained a network for images, and now you're passing a new image to it, and you wanted to classify that image.
What I have a hard time understanding is that like two proteins can have different number of nodes.
Right.
How do you embed them to the same, because you want to measure some sort of distance, right? How do you embed them to the same dimensional vector?
Just by having different.
Okay.
So I think just a clarification for the protein-protein interaction, a node in the graph represents a protein.
Okay.
Okay, and the graph represents some maybe human tissue, for example, right?
Okay.
And you want to label the nodes. You have
so the nodes are not the atoms.
No, it's a protein. And you have to label these nodes, right? And you train it on a human tissue, for example, that's represented by a graph, and then you go to another graph representing another tissue, and you try to label the node. So this is a node classification problem, not a graph classification problem.
Okay.
Sorry, my bad.
Can you go back to the results? Maybe I missed this because I was listening on and off. Any guess for the citation data set? Any guess why max pooling is better than the LSTM, which is better than, I can't really see, Ming, which is better than GCN?
No, go ahead.
Okay, so LSTM is nonsense here, to be completely honest with you, because you're taking away ordering. So they made an unordered LSTM, which is, in my opinion, nonsense. So I don't know why you would ever do that, to be honest. That's a better question. The pooling thing is probably better because there's actually a fully connected network before they're doing max pooling. So you're taking either an average, which is a good baseline, or you're taking a fully connected network that's outputting to a max pooling layer, which is a more, so you're actually getting complex nonlinear aggregation instead of a somewhat trivial.
Are you
function
saying,
mapping is
are you
more
saying
complicated.
simply because pooling has more parameters?
Sure. It's a more powerful function that you're using as your aggregator. Maybe that's a better way to do it.
Also to mention that it performs well on these test cases, but there might be other test cases where mean performs better.
It could be, yes. Yeah.
And depending on the noisiness of the data and whether it's representative of the features, for example, when you have this Twitter data which is quite noisy, when you try to capture that features with a good resolution, with, for example, much powerful max pooling, it may capture noise better than the information that you will try to get. But
it is true. However, I think it's worth keeping in mind. You got to think of exactly what's happening in the embedding, right? So you have an embedding, which is basically a vector with a bunch of parameters, and each of the parameters have relationships between each other that are as yet unclear, right? When you pipe that through a fully connected layer, with what in any sort of context, you're allowing any one of those indices to be related to any other one of those indices. In a pure mean sense, you're doing an element-wise mean, which means that the only relationships that are allowed in terms of those embeddings is from indexed across the indexes. So the type of relationship that you're actually describing is a lot more complex than in the pure mean case. That's not to say that the mean still might not be better.
Depending on the context.
I think it's just saying that you're doing something that's slightly different.
Right.
That's all I thought.
What do you think of having a mean after the fully connected?
Instead of max pooling?
Yes.
I think the main critique there would be that it's not nonlinear, right? So the types of functions that you could describe would be more limited. It's not to say again that it wouldn't work, but remember nonlinearities are one of the big, it allows you a larger function space instead of what you would get in other ones, right? You're also kind of, I guess the other thing you'd be doing is you're overloading more work earlier on in your system as well, right? Because the nonlinearity could exist, but it would be earlier in the pipe in terms of how you're doing the aggregations or something like that.
I couldn't capture that.
So what I'm saying is if you don't have a nonlinearity at the end in the max pooling step, then you're forcing the network to produce any nonlinearities that exist in the system earlier in the pipe, somewhere else. So in that weight matrix, for example, like it has, if there is any nonlinearities, they have to exist. So you're making the network do it somewhere else, right? Anyway.
In the max pooling case, does the order of the neighbor matters?
No, max pooling is invariant to the order.
Because I don't think it matters, yeah.
Because you're taking the max of the contents, right?
Yeah.
So, for example, if you select 179 or 197, then the 9 would be the max, right?
But W is a matrix, am I right?
Yeah, so I don't know how they made it so that the matrix wasn't, but I thought I remember reading that they said it didn't matter. It may be that they're doing it with pairs, right? Or they're concatenating, I don't know. In theory, order could matter, but I think they say it doesn't.
So the matrix is a special kind of matrix.
I would have to look.
Whoa. Actually, I'm not sure. I cannot answer you.
Can I ask a clarification question? Could you remind me how did the LSTM work again? So what were the items in the sequence?
The samples, the sample nodes that you have.
Each sample.
Yeah.
So you sample twice.
No.
It's right there. Unordered set by applying the center and permutation.
You have sampled them and then you put a random permutation of them. So now it's a sequence. Then you pass it through LSTM.
It's a strange thing to do.
Yeah.
Do you have any justification for using
I don't have.
But every learning iteration, the order will differ, and the idea is that it should be invariant to ordering. So you're gonna somehow, after many iterations, force it to be invariant to ordering.
So they're trying to do a by LSTM, but in sequence, because each node doesn't have the context of the other node. That could be the intuition.
Yeah, but I think with the bi-LSTM, the idea is that ordering information does matter. It just matters in both directions.
But if you do this node and then the other node.
But like, it would be like.
Yeah.
I mean, I don't think you're wrong, but it's weird.
Yeah, I'm just trying to be compassionate.
I think the reason why is if you think of it in a purely computational sense, you put in a bunch of embeddings and you get out one, and that's an aggregation. So in a purely computational sense, it actually meets the requirements of what they needed at the thing to do. It does aggregate. You're just not exploiting ordering information. Right? I mean, you could always you could also add them together.
Yeah, you can throw convolution. Yeah. Is it because you don't know n, like the number of nodes? That is why like LSTM is the only thing possible here. But you don't want order to play a role, so you randomize it. Is that rationale?
I think the strength of certain types of LSTMs is that it's not fixed size, yeah, for sure.
No, but here they say if the sampling size is greater than the amount of nodes that you have, you sample with replacement.
Okay, that makes sense.
Yeah, I mean, it's also really interesting because I think one of your discussion questions was about sampling, and there are actually lots of there are a number of functions that you can, or algorithms that you can use over a graph that will give you an ordering, right? Based on proximity, there's a whole bunch of different ways you can do it, and some of them are blazingly fast. So it could be ordered. That was a design decision that they decided that the neighbors shouldn't be ordered based upon the type of sampling that they're doing. You could actually have an ordering.
Can you elaborate on it?
Well, like you could, the simplest ordering would be based on proximity. I have the top 10 neighbors, right? But some of those neighbors might be closer than others, assuming that there is any kind of additional structure that you have in terms of that, right? Now, again, I think in Twitter, notions of proximity would be vague. Right? You'd have to quantify that somehow.
When you have a multi-relational graph here, that would be the case. Because based on, for example, the information that you have on the, for example, the other relation between, for example, you have Twitter and also you have the information, I don't know, about their ages or something like that. They are somehow connected as well. So that way, based on the other information, you have already a Euclidean space that you can have a proximity.
Measure the distance between the initial representation, initial embeddings that you're using, and then use that initial information as a proximity.
Right.
But like I was thinking, maybe the reason that they use LSTMs and they just use permutation is that they just thought that in the order doesn't matter, like it's a graph.
Right. Yeah. But LSTM is somehow, sensitive to the ordering, right? That's
so why? Yeah,
I just
why
think,
pick it in the first?
Yeah, I would just think like as soon as you say LSTM, you're like, I care about order, and then you're like, but I don't.
Yeah, so that's why I went to the second order estimation of perhaps they want to implement a by LSTM, but anyhow,
I mean,
I'm being
terrible.
Sorry. Yeah.
It would work, and I mean, I think if you look at the scores, it wasn't that much worse, was it?
It was actually better than some, right?
So yeah, it had one of the highest scores in the case of the unsupervised Reddit thing.
But they're a bit close, actually. You see.
Yeah,
all of them are close. Yeah.
So I mean, it does work.
Yeah,
it's just weird.
Yeah, I still have another disambiguation about the output of this network. Okay. What is it?
Wow.
like when you, after all, we train everything.
Right.
We give it another inductive, right? It's inductive, so we give it another node. What is the output and how can we use it actually?
A vector embedding.
No parallel.
Right.
So
a vector embedding that is in the Euclidean space that you can, that you can assign a label to it because. Okay. No. Not okay.
It sounds like an insurance problem almost. Like they're making products now where, given access to somebody's social network, you want to assign somebody a score for their mortality, and you see what the risk type behaviors are for the friends of that person, and then use that to judge the person themselves. And it sounds like that network is for that sort of thing.
So you have unlabeled neighbors. You want to classify them.
You have labeled neighbor, or some neighbors are labeled. The main node isn't labeled, and you want to label the main node based on, you want to judge somebody based on what the friends do, basically.
Yeah. Or another situation would be that you have a system which is growing, so nodes are being added to the system, and you want to classify those, and you want to have a kind of embedding which can actually you want to be able to produce embeddings for those nodes that you've never seen.
So you have a vector to represent that node that I've given to it.
Exactly.
But the thing is, what is that vector? What does it mean?
It has the information about it's actually a good representation of what this new node means to me. This new node has these means to the task.
What is the meaning of meaning that you're trying to get? That's the question.
In the case of Reddit, aren't you trying to predict the category of the Reddit post, right? I think you mentioned in the previous slide what exactly you're trying. So classifying Reddit posts as belonging to different communities. Yeah. So probably you're trying to see what community does a node belong to.
Okay.
Yeah, but this network just outputs an embedding for the nodes, right? Then you use that as input to another classifier.
That's exactly the disambiguation between the application of it.
So that's why there are two columns, unsupervised and supervised. One, you do an unsupervised learning of the embedding and then use that in a machine learning classifier downstream. And the other one is that you do a supervised learning where you learn directly to classify it. So learn the embedding in a pipeline which directly classifies the node.
Yeah. Okay. Can we see the results again?
Yeah.
Thank you.
You have to.
Okay. So that's why the right side is always better. Okay. Of course. Okay. The right side is always better than the left. Yeah.
Yeah. So you're basically saying I'm informing my representations with the actual task that I care about.
Yeah.
Okay. Thank you.
Thank you for your time, I guess.
Thank you.
Thank you.